In this next set of videos, we're going to predict the shapes of molecules and ions by using VSEPR, which is an acronym for valence shell electron pair repulsion. And really all this means is that electrons being negatively charged will repel each other. Like charges repel. And so when those electrons around a central atom repel each other, they're going to force the molecule or ion into a particular shape. And so the first step for predicting the shape of a molecule or ion is to draw the dot structure to show your valence electrons. And so let's go ahead and draw a dot structure for BeCl2. So you find beryllium on the periodic table. It's in group 2, so 2 valence electrons. Chlorine is in group 7, right? And we have 2 of them. So 2 times 7 is 14, and 14 plus 2 gives us a total of 16 valence electrons that we need to account for in our dot structure. So you put the less electronegative atom in the center. So beryllium goes in the center. We know it is surrounded by 2 chlorines. So we show beryllium bonded to 2 chlorines here. And we just represented 4 valence electrons. So here's 2 valence electrons, and here's another 2 for a total of 4. So instead of 16, right, we just showed 4. So now we're down to 12 valence electrons that we need to account for. So 16 minus 4 is 12. We're going to put those leftover electrons on our terminal atoms, which are our chlorines. And chlorine is going to follow the octet rule, right? Each chlorine is already surrounded by 2 valence electrons, so each chlorine needs 6 more. So go ahead and put 6 more valence electrons on each chlorine. And since I just represented 12 more electrons there, now we're down to 0 valence electrons. So this dot structure has all of our electrons in it. And some of you might think, well, why don't you keep going? Why don't you show some of those lone pairs of electrons in chlorine moving in to share them with the beryllium to give it an octet of electrons? And the reason you don't is because of formal charge. So let's go ahead and assign a formal charge to the central beryllium atom here. So remember, each of our covalent bonds consists of 2 electrons. So I go ahead and put that in. Right? And if I want to find formal charge, I first think about the number of valence electrons in the free atom, and that would be 2 for beryllium. So we have 2 electrons in the free atom, and then we think about the bonded atom here. So when I look at the covalent bond, I give one of those electrons to chlorine and one of those electrons to beryllium, and I do the same thing for this bond over here. And so you can see that it is surrounded by 2 valence electrons. 2 minus 2 gives us a formal charge of 0. And so that's one way to think about why you would stop here for the dot structure. So it has only 2 valence electrons. So even though it's in period 2, right, it doesn't necessarily have to follow the octet rule. It just has to have less than 8 electrons. And so again, formal charge helps you understand why you can stop here for your dot structure. Let me go ahead and redraw our molecule so we can see it a little bit better. And we'll go ahead and move on to the next step. So let me go ahead and put in my lone pairs of electrons around my chlorine here. So we have our dot structure. All right, next we're going to count the number of electron clouds that surround the central atom. And I like to use the term electron cloud. You'll see many different terms for this in different textbooks. You'll see charge clouds, electron groups, electron domains, and they have slightly different definitions depending on which textbook you look in. And really the term for me, the term of electron cloud helps to describe the idea of valence electrons in bonds and in lone pairs of electrons occupying these electron clouds. And you can think about them as regions of electron density. And since electrons repel each other, right, those regions of electron density, those clouds, want to be as far apart from each other as they possibly can. And so let's go ahead and analyze our molecule here. So surrounding the central atom. So we can see that here are some bonding electrons right here surrounding our central atom. So we could think about those as being an electron cloud. And then over here we have another electron cloud. So we have 2 electron clouds for this molecule. And those electron clouds are furthest apart when they point in opposite directions. And so the geometry or the shape of the electron clouds around the central atom, if they're pointing in opposite directions, it's going to give you a linear shape here. So this molecule is actually linear because we don't have any lone pairs to worry about here. So we're going to go ahead and predict the geometry of the molecule as being linear. And if that's linear, then we can say the bond angle, right? So the angle between the chlorine, the beryllium, and the other chlorine is 180 degrees. So just a straight line. All right, so that's how to use VSEPR to predict the shape. Let's do another example. So CO2, so carbon dioxide. So we start off by drawing the dot structure for CO2, right? Carbon has 4 valence electrons, oxygen has 6, and we have 2 of them, so 6 times 2 gives us 12. 12 plus 4 gives us 16 valence electrons to deal with for our dot structure. The less electronegative atom goes in the center, so carbon is bonded to oxygen, so 2 oxygens like that. We just represented 4 valence electrons, right? So 2 here and 2 here, so that's 4. So 16 minus 4 gives us 12 valence electrons left. Those electrons are going to go on our terminal atoms, which are our oxygens, which are going to follow the octet rule, right? So each oxygen is surrounded by 2 electrons, so therefore each oxygen needs 6 more valence electrons. I'll go ahead and put in 6 more valence electrons on our oxygen. Now, you might think we're done, but of course we're not, because carbon's going to follow the octet rule. Carbon does not have a formal charge of 0 in this dot structure. So even though we've represented all of our valence electrons now, we need to give carbon an octet. We need to give carbon a formal charge of 0. And we can do that by moving in this lone pair of electrons into here to share those electrons between the carbon and the oxygen, and also with this lone pair of electrons. So we move those in like that. And now we can see that carbon is double bonded to our oxygen. So now our dot structure looks like this. And each oxygen, instead of having 3 lone pairs of electrons, now each oxygen only has 2 lone pairs like that. So there's our dot structure. So let's go back up here to look at our steps for predicting the shape of this molecule. Right, so step 1 is done. Draw a dot structure to show the valence electrons. Next, we're going to count the number of electron clouds surrounding our central atom. So we go back down here and we find our central atom, which is our carbon, and we think about the regions of electron density that surround that. So we can count this double bond as a region of electron density because we're not worried about how many electrons are there. We're just worried about the fact that there is a region of electron density. So that's one electron cloud. And then over here we have another electron cloud. So we have 2 regions of electron density. We have 2 electron clouds here, which are going to repel each other, right? So when we look at step 3, predict the geometry of the electron clouds, right? Predict the geometry of the electron clouds around the central atom. Well, those electron clouds are going to be opposite to each other, right? They're going to point in opposite directions. So once again, they're going to force this molecule into a linear shape, right? So the carbon dioxide molecule is also linear with a 180-degree bond angle. So once again, we don't have any lone pairs of electrons on our central atom, so we don't really have to worry about that, and we can go ahead and predict the geometry as being linear. So that's how to approach it. Draw the dot structure, think about electron clouds, and think about the shapes of your molecules. In the next video, we will look at how to approach 3 electron clouds.